Okay, we're gonna make a start. If you could find your seats, please. All right. So this is clearly a really popular session. Very, very good to see you all in here. We're going to make a start now. So welcome to the room, this room for the Energy Innovation Base Camp morning sessions. We've got 4 fantastic speakers presenting problem statements to you. You don't want to hear from me, you want to hear from them. So I'd love to introduce Anna from the National Energy System Operator, who's going to take you through NTO Stability. Over to you, Anna.
Thank you. Good morning, everyone. So I'm Anna Blackwell. I'm a product manager within NESO, within our network control program. So we're responsible for the situational awareness tools that are going into our control room and making sure they have the optimum solutions that they can use within our control room. In particular, I'm responsible for delivering a new set of tools around network topology optimization. So this is something we're looking to move into in the future. And we have a number of problem statements today that we are launching around this subject. The first 2 of this morning's sessions. So the one I'm going to cover now is around stability solvers, and then the one following this will be around AC, and then there's a later one that my colleague Ian Dytham will be presenting on visualization later on this morning. So for anyone who isn't aware, the National Energy System Operator, or NESO, is responsible for planning and delivering energy across Great Britain. As part of that role, we operate the GB electricity system, and we need to ensure that that system is reliable, economic and secure for all credible faults on the system. And that's becoming an increasing challenge as we move towards and move away from the traditional large fossil fuel generation that was on the system and move towards a lot more smaller, sustainable, but less predictable generation that is spread out across both the distribution and the transmission systems. So to give a bit of background into the problem that we're launching here, a key role of the transmission system is to route power from generation to demand. The system that we operate is really, really complex. There are multiple routes to ensure that electricity gets from A to B, and electrons like the path of least resistance. They want to go the quickest route they can from A to B. Bit like if you think about the road network. If you want to get from Edinburgh to London, you're most likely to pick the motorways. And then as you get down into at the very start of your journey or the very end of your journey is where you start to move on to the smaller roads. That's the quickest way to get from A to B. That's where you prefer to do it. However, if there's roadworks, or there's an accident and those motorways are closed, or they get reduced in their capacity, they quickly come to a standstill and you start to look for alternative routes around the system. That's kind of how the electrons work around the electricity system, if you need to visualize how it works. And any fault that occurs on the network or any outage that's on that network can cause overloads on the equipment or cause unacceptable voltage or stability conditions. For us to resolve those situations, we often need to end up redispatching generation. That results in significant costs of constraining generation. However, we can reduce some of that. We can alter some of the amount that we need to redispatch by adjusting the topology of the network through either substation reswitching or changing the circuit impedances by tapping QBs and forcing the electricity through a different route. When we consider the security of the system, we have to cater for any fault that could occur. That could be a cable fault, overhead line, switch, transformer, protection faults. All of those are potentially credible on our system, and we have to make sure that we can deal with any one of those occurring at any time of the day or night. Along with changing generation patterns, demand patterns, outage patterns, that gives us hundreds, thousands, millions, and possibly billions of different scenarios that we have to look at to ensure that on a minute-by-minute, second-by-second basis, the power system is secure. Our current process is extremely manual. Engineers assess different configurations to determine the most optimal running at any one point of the day. They're using analytical tools, but they are having to reassess and readjust the way that the studies are set up continuously to adjust that. As things change in real time, it means our optimal running arrangements are a moving goalpost. What works now, or what works for tomorrow at this moment in time, and for the worst case scenario tomorrow, may not actually be the same in an hour's time or in 2 hours' time because something has changed. As a result, we want to bring in a layer of technology that can assist engineers with identifying these reconfigurations more rapidly, more accurately across the different timescales, and understand how those fit across different time blocks. We ultimately want to optimize the network before we need to approach the market and redispatch generation. This might sound simple, but those large number of variables that we're looking at mean there's potentially billions of scenarios that need to be considered. So the problem we have at the moment is the tools that we've got available to us are not quick enough for us to manage the number of scenarios we need to look at. Even if we can identify a small number of scenarios that need to be considered, it still takes a significant amount of time for our analysis to take place. Most of the fast power flow analysis tools at the moment are DC. They will purely look at, if you want to get the electron from A to B, what does it do from a thermal point of view? That'll show us where we've got basic overloads, but the changing dynamics of the system mean we now need to be optimizing much more for dynamic stability, voltage conditions, as well as the thermal provision. Especially as we move away from conventional rotating generation and move to much more inverter-based generation sources and change in demand as well. So historically and currently, we often will optimize from a DC point of view and then focus in on a worst case scenario and individual locations to validate that the solution that we've come up with works from an AC point of view and from a stability point of view. Going forward, we need to be able to study the whole network and optimize from a stability point of view, because optimizing one area may actually create a problem elsewhere, and we're more likely to miss some of those scenarios. This requires a new maturity of stability assessment tools, and that's what we're bringing here to launch today. What we're interested in is what new techniques could exist for us to look at the stability on the network, how that can speed up that analysis so that we can be using it in near real time. So we're talking about planning for tomorrow, planning for next week, even down to could we use it in the control room to see what's going to happen in an hour's time, 2 hours' time. It's not appropriate to spend 2 hours running something if we need to know an answer for something that's about to happen. Or if a fault's just occurred in the system, how do we re-secure something that's happening now? It's really, really critical to us to be able to run a large number of scenarios as quickly as possible in those near real-time scenarios. So what are we looking for? We want basically new methods, new technologies that could optimize how those algorithms work at the moment. Ideally, we'd like things that can build on our current modelling tools, so can take a network model that's either come out of our SCADA tools or comes out of our current planning tools, such as Dig Silence Power Factory. But we're open to suggestions in any way. We're looking at things that can either already exist out there that we're not aware of, or things that are and can just be in sort of a tested product stage, or ideas and research of areas that we could look into that could help speed up and improve the way we're looking. We're looking for sort of plans and ideas, the plans along those rather than just an idea that we can work into, and the solutions that work from that way. And to give us a bit more background in where we're going and what we've done in this area, we ran an NIA study into network topology optimization earlier last year. There was a report on the status of network topology optimization across the world that is available both on the ENA's website and our own innovation website, so NESO's innovation website that will give a better idea and understanding of the sorts of work that has been done already. Most of the work that's happening around the world at the moment is focused on those DC analysis and speeding that up. This is something that it's not just us as NESO or even in Great Britain network is interested in. This is something that worldwide people are looking for now, TSOs are looking for around the world to try and improve their capabilities. Okay. I think that's everything. It says any questions on here, but I think the question and answer session is coming up later.
It does. If you just click forward one slide, there may be the Slido QR. I'm hoping there's a Slido QR code just there. So you can use that Slido QR code to put your questions in. You'll need to look for Edward room 5 and 6, which is this room here, and then you can post your questions in the Slido. We'll also be running all the presentations back to back, and then we'll do a Q&A at the end. So you can, if you want to ask your question verbally, you can raise your hand. We have a roaming microphone to come and make sure we get the answer. Please do speak into that microphone because we're recording the sessions. We want to make sure we've captured the question as well as the answer. So we're doing that at the end once you've heard all 4 presentations. Now, I know, Anna, you're next up for the next presentation as well. So I imagine most people in the room want to listen to that, but if you were really keen to go to another room, we have a 5-minute changeover time starting right about now. So if you do need to go to another room, you can do that, and we'll wait for others to come to this room as well. So we're just spending a couple of minutes just changing rooms now. Thank you.